Okay, so now continuing with question number 11. So what we can do is that I can create some matrices here. For example, A as 2, 1, 1, 2, 1, 1, 1, negative 2, negative 1, 1, negative 2, negative 1, and 0, 3, negative 5. And then you can also create the matrix X as X, Y, and Z. And so you have 2, 1, 1, 1, negative 2, negative 1, and 0, 3, negative 5. And your matrix B would be 1, 3 halves, and 9. So then once you have this, you need to calculate basically a determinant A. And determinant A is determinant 2, 1, 1, 1, negative 2, negative 1, and 0, 3, negative 5. And that's the same thing as basically expanding along the first row. You have negative 1 raised to the second power times 2 times the determinant. So basically deleting this row and this column, you get negative 2, negative 1, 3, and negative 5, plus negative 1 raised to the third power times 1 times the determinant, delete this column, this row, 1, negative 1, 0, negative 5, 1, negative 1, 0, and negative 5, plus negative 1 raised to the fourth power times 1 times the determinant 1, negative 2, 0, 3, 1, negative 2, 0, 3. And then you have basically negative 1 raised to the second power is equal to 1. So you have 2 times negative 2 times negative 5 is 10 minus negative 3. And here you have negative 1 to the third power is negative 1. So minus negative 5 times basically minus 0. And here you have negative 1 to the fourth power is 1, so plus 3 minus 0, so that's just a 3, which is equal to, now this is 10 plus 3 is equal to 13, 2 times 13 is equal to 26, plus 5, plus 3, and that's basically 26 plus 8, 36, 34. And that is not equal to 0, which means that therefore basically A is a non-singular matrix, and therefore A inverse exists. And so you can say that basically you can say that the system of equations basically is consistent and you will have a unique solution. You will have a unique solution. Now, in order to get that solution, we know that the solution is is x is equal to A inverse times B. Now to calculate A inverse, you need to write A inverse as basically the adjoint of A divided by the determinant A. The adjoint of A divided by the determinant A. And so first we need to find the adjoint of A. Okay, so now what basically in order to calculate in order to calculate A inverse, we need the adjoint of A and divide that by the determinant A, and this is the matrix A. Now there is something that I might have actually done wrong in at least one of the exercises that I've done in this chapter, and I don't know how, but for whatever reason I was under the impression, and I don't know when that happened, because definitely the first time that I used or that we basically learned the concept of the adjoint of a matrix, well, we did everything of course right, but somewhere along the way I have and this kind of thing happens in your mind. Sometimes it happens unconsciously. So I was under the impression that when you want to calculate for example, the cofactor of this element, that you would write, for example, A of 1, 1 as basically -1 raised to the power, for example, 1 plus 1 times the element itself, which is 2, times the minor of this element, which is this determinant -2, -1, 3 and basically -5. This is wrong, because this is not supposed to be there. Basically, by definition, basically the adjoint, so the minor of a so I repeat this one more time, so that we, if I have confused you as well, I need to deconfuse you, right? So basically, if you have some matrix, for example, this matrix over here, as a definition, what we said, definition number 1, we said that the minor of an element A, the minor of an element A of ij, of an element A of ij, of a determinant obtained, I'm sorry, not of a determinant. So we said that basically the minor of an element A of ij of a determinant is a determinant obtained by deleting its ith row, deleting its basically ith row and jth column in which the element A of ij lies, and the minor of an element and the minor of an element A of ij is denoted by basically M of ij, right? So again, as a definition number 1, we said that the minor of an element A of ij of a determinant is the determinant obtained by deleting its ith row and jth column in which the element A of ij lies, and the minor of an element A of ij is denoted by M of ij. And basically, for example, what that means is that, for example, if you have this determinant delta, which is equal to, for example, 1, 2, 3, 4, 5, 6, and 7, 8, 9, if you want to find the minor of the element 6, which is M of basically 2, 3, that is equal to basically the determinant that you would get by deleting the ith row and the jth column, meaning that the second row and the third column, and you would get 1, 2, 7, 8. 1, 2, 7, 8, which is equal to basically 8 minus 14, which is equal to -6. So this is basically the minor of an element A of j of a determinant, right? Now, as another definition number 2, we said that basically the cofactor of an element A of ij, the cofactor of an element A of ij, denoted by A of ij, denoted by capital A ij, is defined by basically A of ij is equal to -1 raised to the power I plus j times the minor of ij. Now you can see that basically the element is not here, and basically you can say where M of ij is the minor of A of ij, right? So this is the definition of a cofactor. So now we can go back to the example that the problem that we had here, and solve the problem. And I don't really know where or how I came to this conclusion that I don't really know how that happened, except that I noticed that I was doing something wrong in one of the exercises, and then I checked a couple of solutions and I saw that the solutions were all alike, and so the only thing that I could assume was that I was doing something wrong, and I went back to the definitions and I said that I was actually wrong. So I don't know how that happened. It's actually okay. Now if I go back to the exercise, we were working on this exercise, and then we said that we wanted to find the basically the adjoint of A. Now the adjoint of A, let me take a look at the definition again. Okay, so now the adjoint of A is the matrix that you get by calculating the cofactor of each of these elements and taking the transpose of that matrix, and that would be the adjoint of A. So now over here, in order to calculate the cofactors here, I will write A of 1, 1 is equal to negative 1 raised to the power 1 plus 1, which is equal to 2, times this times the minor of, let me write this over here, times the minor of 1, 1. Okay, I can calculate the minor of 1, 1. I can calculate for example, the minor of, I can calculate m of 1, 1 as basically deleting the first row and the first row and the first column, and then I get the determinant here. So so that would give me a determinant as negative 2, negative 1, 3, and negative 5. And that means that then you have, now to take a look at the solution here. Okay, so okay, so now the minor of m of 1, 1 is equal to m of 1, 1 is equal to this determinant, and therefore you have negative 2 times negative 5 is equal to 10 minus negative 3, which is equal to 10 plus 3, which is equal to 30. Now m of, for example, m of or we can do all of them directly without having to calculate the minors first. So the cofactor A of 1, 1 is equal to negative 1 raised to the power 1 plus 1, which is equal to 2, and the minor, which is, and the minor of 1, 1, which is delete the first row, the first column, negative 2, negative 1, 3, and negative 5. And then you have basically positive 1 times basically negative 2 times negative 5 is equal to 10 minus negative 3, which is equal to 10 plus 3, which is equal to 13. Now A of 1, 2 is equal to negative 2 raised to the third power times this determinant, which is delete this column, delete this row, 1, negative 1, 0, negative 5. 1, negative 1, 0, negative 5. And then you have basically negative 1 times basically negative 5, and that is equal to positive 5. Now A of 1, 3 is equal to negative 1 raised to the fourth power times this determinant. So 1, 3, delete this column, delete this row, 1, negative 2, 0, 3. 1, negative 2, 0, and 3. And that is equal to, this is positive 1 times 3 minus 0, which is equal to 3. Now A of 2, 1 is this, is basically equal to basically so negative 1 raised to the power 2 plus 1, which is equal to 3 times this determinant 2, 1. So delete this column, delete this row, 1, 1, 3, 1, 1, 3, and negative 5. And so you have, basically negative 1 raised to the third power is negative 1 times negative 5 minus 3, Negative 5 minus 3, that's negative 8 times negative 1 is 8. Now a of 2 is equal to negative 1 raised to the 4th power times the determinant, delete this row, delete this column, 2, 1, 0, negative 5, 2, 1, 0, negative 5, which is equal to 1 times negative 10, which is negative 10. Now a of 2, 3 is equal to negative 1 to the 5th power times the determinant, so 2 and 3, delete this column, delete this row, 2, 1, 0, 3, 2, 1, 0, 3, and that there you have negative 1 times basically 6, which is equal to negative 6. Then you have basically, then you have a of 3, 1, which is equal to basically negative 1, which is equal to negative 1 raised to the power 4 times this determinant 3, 1. So delete this column and delete this row. 1, 1, negative 2, negative 1. 1, 1, negative 2, negative 1. And so you have 1 times negative 1 minus negative 2, which is equal to negative 1 plus 2, which is equal to 1. A of 3, 2 is equal to negative 1 raised to the 5th power times the determinant 3, 2. So delete this column, delete this row. 2, 1, 1, negative 1. 2, 1, 1, negative 1. And so you have negative 1 times negative 2 minus 1, which is equal to negative 3 times negative 1 is equal to positive 3. And finally, a of 3, 3 is equal to negative 1 raised to the 6th power times the determinant, delete this column, delete this row, 2, 1, 1, negative 2, 2, 1, 1, negative 2, which will give you basically 1 times negative 4 minus 1, which is equal to negative 5. Now, I will write all of these numbers arbitrarily in some matrix. For example, D, I will write them as 13, 5, 3, 13, 5, 3, and 8, negative 10, 8, negative 10, and negative 6, and then I have 1, 3, and negative 5. 1, 3, and negative 5. That is basically the matrix that we get. Now let me check if my matrix is okay. 13. Oh, okay. Now if I take the transpose of this matrix, D transpose, what I will have is, and this is a matrix of course, if I take the transpose of this matrix, I'll get 13, 5, 3, 8, negative 10, negative 6, and 1, 3, negative 5. So you have basically 13, 8, 1, 5, negative 10, 3, and 3, negative 6, and negative 5. This is the right matrix, and this is now the adjoint of A. This is the adjoint of A. So if you paid attention to this process, what we did was that this was the matrix A. So I calculated the cofactor of each of these elements. Here. The cofactor of each element, for example, A of 1, 1, the cofactor of this element is negative 1 raised to the power I plus j, for example, 1 plus 1, times the minor of the same element. The minor of the same element is basically the the matrix that you would, the determinant that you would get by deleting the ith row and the jth column, the ith row and the jth column, and you would get this determinant, which is -2, -1, 3, and -5. And then you can calculate, you'll get some number for that. Now, once you calculate all of those cofactors, you will put all of those cofactors arbitrarily in some matrix. For example, you can call it D, and you will write your matrix over here. Then if you take the transpose of that matrix, the transpose of that matrix, which is made from all of these cofactors of the elements of A, the transpose of that matrix is going to be the adjoint of A, right? So that is the adjoint of A. Now, once you have the adjoint of A, and once you have the determinant of A, which is in this case 34, so you know that the determinant of A is equal to 34, right? So then A inverse is the same thing as basically is 1 over determinant of A times the adjoint of A, which is equal to 1 over 34 times the adjoint of A, which is basically this matrix, 13, 8, 1, 5, -10, 3, 3, -6, and -5, and that is basically A inverse. So A inverse is equal to 1/34, 13, 8, 1, 5, -10, 3, and 3, -6, and -5. One of the examples that I did in one of the previous videos, I did make that mistake. I apologize for that. But there is no way for me to go back, please. Excuse my... It was not about carelessness. Sometimes you make some conclusions, and those conclusions turn out to be not right, and so you have to take them back. So there is no other way to learn, really. So that is basically that. Now, so this is A inverse. Now we said that basically X is the same thing as A inverse times B, and B is equal to 1/3/2 9. 1/3/2 and 9. So we said that B is a matrix as 1/3/2 and 9. So if X is the same thing as A inverse times B, then that must be equal to basically this matrix, which is A inverse. So you have 1/34 times 13, 8, and 1, 5, -10, and 3, 3, -6, and -5, and so times, this is A inverse times B, which is basically 1/3/2 and 9. So there you have a 3×3 matrix, there you have a 3×1 matrix, which gives you a 3×1 matrix, of course. So you have 1/34 times, so 13 times 1 is equal to 13, 8 times 3/2 is equal to 4 times 8 divided by 2 is equal to 4, 4 times 3 is equal to 12, and 1 times 9 is equal to 9. 5 times 1 is equal to 5, -10 times 3/2 is equal to 10/2 is equal to 5, 5 times 3 is equal to 15, negative 15. Negative 15. And then you have 3 times 9 is equal to 27. Then you have 3 times 1 is equal to 3. 6 halves is equal to 3. 3 times 3 is equal to 9, so negative 9. And negative 5 times 9 is equal to negative 45. Right, so that is that. That is equal to 1/34. That is equal to 1/34. 1 divided by 34 times, so you have 13 plus 12 is equal to 25. 25 plus 9 is equal to 34. 34. 27 plus 5 is equal to, so you have 27 plus 5, which is equal to basically 12, 32. 32 minus 15 is equal to 2 and 12. So you have 17. 17 plus 15 is equal to 20 and 12, 32. Okay, so that's a 17. And then negative 45, negative 9 is equal to negative 54, and plus 3 is equal to negative 51. So that's negative 51, and these are all divisible. Now, if you do this operation, what you will get is 34 divided by 34. So I can write it over here, for example. 34 divided by 34 is 1. 17 by 34 is basically 1/2. 1/2, and negative 51 by 34 is equal to, I think 3 times 17 is equal to, so negative 51 by 34 is the same thing as, I think, 2/3, I suppose. No, 3/2, I suppose, because 2 times 17 is equal to 34. 3 times 17 is equal to 30 and 21, 51. So 51, I can write it as 3 times 17, and I can write this as 2 times 17. 17 and 17 will cancel out, negative 3/2. So that is equal to x. And that x, by the way, is equal to x, y, and z, of course. You already know that. Which means that, basically, x is equal to 1, and y is equal to 1/2, and z is equal to negative 3/2, which is exactly what we saw in the graph. I said that basically the solution is going to be in the 5th octant. The 5th octant is basically down here. So if you imagine that this is basically the y-axis here, and this is the z-axis, and this is the x-axis. So when your x is positive, you are along this is the positive x-axis. Your y is positive, you're along the positive along the positive y-axis. Your z is negative, that means that you are in the, let me show you somewhere over here, because there is no way to see it actually. You see over here, basically these are the positive x's, and these are the positive y's, and these are the positive z's, right? Now when you Now you have 8 octants here. This is the first octant, this is the second, the third, the fourth, and the fifth comes below the first octant, below this plane that you can see here, below this gray plane, right? Now you can see that the point of intersection of these you can see that basically these two planes, this plane over here and this plane over here, they have some point of intersection down here, not point but the line of intersection, and this plane is going through that line of intersection exactly over here, which corresponds to, for example, which corresponds to somewhere about -1.5 on the z-axis, -1.5 on the z-axis, and on the y-axis it's somewhere about 0.5, which is exactly 1/2 here, and on the x-axis it's about 1. It's somewhere about 1, I suppose, right? It's somewhere about 1, which is exactly 1, as you can see. So you are in the fifth octant. And again, these octants are, so looking at the coordinate system from the top, and this being the positive y-axis, this being the positive x-axis, and this being the positive z-axis, looking from the top, this is the first octant, this is the second octant, the third, the fourth, and the fifth octant comes down here, and then you have to go back to the sixth octant, seventh octant, and eighth octant, all on the bottom of the coordinate system. Okay. All right. So that was basically that. Now, this was question number 11. Let's see what we have in question number 12. Okay, so the next question that we have is question number 12. So question number 12, we have another system of equations, which is x minus y plus z is equal to 4, and you have 2x plus y minus 3z is equal to 0, and x plus y plus z is equal to 2. So you have this system of basically equations, and we want to know whether there is a solution or not. So let's graph them first. Let's see what happens if we graph them. And of course you need to be familiar with these graphs, because when we get into calculus, you need to actually be able to read these graphs efficiently, and you need to be able to, meaning that you need to be able to read and understand these graphs efficiently, because when it comes to calculus, then these graphs are going to be curves, and basically there is a top hill, there is a downhill, there is all kinds of things in these graphs, and if you can make sense of those things properly, then you will be very efficient in calculus, and you will be very efficient in other branches of science. For example, then of course calculus is not something that you would learn just for having fun. Of course it's a lot of fun, but you are going to use it somewhere. For example, you're going to use it in physics, and of course you should be able to make sense of it, right? And the best way to make sense of mathematics, for me at least, is graphs, because you take a look at the graph and you see everything is just just in a glance, right? Okay, so I'm going to graph these equations. X minus y plus z is equal to 4. So you have a plane up here, and this is these are the positive y's, these are the negative y's, and this is these are the positive x's. And I'm zooming out, I suppose, right? Okay, so these are the positive y's, these are the negative y's, these are the positive x's, and this is the z-axis, and there you have your plane. The next equation is 2x minus y minus 3z, 2x plus y, 2x plus y minus 3z is equal to 0. And then you will get this other plane, which goes like this. And if I turn this on as well, you have these two planes that intersect basically at this, of course this is the x-axis, so exactly at this along this line basically. And then if you basically have x plus y plus z is equal to 2, x plus y plus z is equal to 2, you will have this plane over here, and let's see if they actually intersect at any point. So the point of intersection is actually they intersect at this point exactly here. This point over here. You see over this point? That is their point of intersection. It's not a line, it's just a point. And so you are actually in the, so this up here, if you start from the right, in front of you, you have the first octant, second, fourth, and the first, second, third, and fourth octant, and this point is somewhere in the fourth octant, meaning that your x coordinate is positive, your y coordinate is negative, and your z coordinate is positive, meaning that only y is negative. Except for that, all the other two are positive, right? So we expect that the solution is in the fourth octant, right? Now let's go to the equations and take a look at them and see how we can actually solve them. So you can create the matrix A, for example, as 1, negative 1, and 1. 1, negative 1, 1, 2, 1, negative 3, 2, 1, negative 3, 1, 1, 1, 1, 1, 1, and so you will have another matrix X as X, Y, and Z, and you will have another matrix B as 4, 0, and 2. 4, 0, and 2. So now if I calculate the determinant A, okay, so now to calculate the determinant A, I can calculate the determinant A as, for example, I could say that, for example, determinant A is equal to, for example, A11 times, for example, A of 1, 1 plus A12, for example, times A of 1, 2 plus A of 1, 3 times A of 1, 3, right? I can do that, but since I don't have the cofactors, I'm going to just simply expand along these rows, along the row 1 for it, the row 1, and just simply calculate the determinant that way. Meaning that I'm going to write this as basically, I'm going to write this as -1 raised to the power, raised to the power, basically 1 plus 1, which is equal to 2 times 1 times basically deleting this row, deleting this column, you get 1, -3, 1, 1, 1, -3, 1, 1, and add to that -1 raised to the third power times -1 times the determinant, delete this column, delete this row, 2, -3, 1, 1, 2, -3, 1, 1, and then you have also -1 raised to the fourth power times 1 times this determinant, delete this row, delete this column, 2, 1, 1, 1. You have 2, 1, 1, 1, and then you have, and then we need to calculate this, whatever that is. So we have -1 to the second power is 1 times 1 is equal to 1. So you have basically 1 times 1 is equal to 1 minus -3 minus -3. Here you have -1 times -1 is +1. So here you have 2 minus -3, and this is 1 times 1, which is equal to 1 times 2 minus 1, 2 minus 1, which is the same thing as basically, which is the same thing as 1 plus 3 plus 2 plus 3 plus 2 minus 1 is equal to 1, which is the same thing as 1 plus 3. So 2 plus 3 plus 1. So you have 1 plus 3 is equal to 4, 6, 6 plus 3 is equal to 9, and 10. So the determinant of A is equal to 10. I'm going to just simply, to save some space, write it over here, 10. This is equal to 10. And let me actually take a look at the solution to just make sure that I'm not making any mistakes. Is equal to 10, right? And this is not equal to 0, which means that basically A is a non-singular matrix, which also means that A inverse exists, and also means that basically the system of equations, is consistent, which means that you will have basically a unique solution. A unique solution. Now, in order to find the solution, of course you know that basically X is equal to A inverse times B, and you know that A inverse is the same thing as the adjoint of A divided by determinant A. So we need to calculate the adjoint of A. To calculate the adjoint of it, we need to find the cofactors of each of these elements. Of course, of these elements primarily, but these are the same elements. There is no difference between them, between the elements themselves. Although this is a determinant, this is a matrix. And so we can start with basically, for example, the cofactor A of 1, 1, which is equal to, and remember that the cofactor A of 1, 1 is, or basically the cofactor A of ij by definition is negative 1 raised to the power I plus j times m of 1, 1. Times m of 1, 1, and this is the minor of 1, 1, meaning that, so that of course you understand that negative 1 raised to the power I plus j, that is clear that you understand it. But m of 1, 1, for example, in this case, would be, for example, a determinant that you would obtain by deleting the first row and the first column, and then you would get 1, negative 3, 1, 1, 1, negative 3, 1, 1, and that would be the minor of this element 1, 1, right? So, and then you can put this over here instead of m of 1, 1 and calculate this part as well, and that would be basically, for example, A of 1, 1, right? So that is basically that. Now, therefore you can say that the cofactor A of 1, 1 is negative 1 raised to the power 1 plus 1, which is equal to 2, times the minor of that element 1, 1, which is this determinant 1, delete the first row and the first column, so you get 1, negative 3, and 1, and 1. And so you will get positive 1 times 1 minus negative 3, which is equal to 1 plus 3, which is equal to 4. So A of, for example, 1, 2 is equal to negative 1 raised to the power 1 plus 2, which is equal to 3 times the minor of this element. Delete this column, delete this row, 2, negative 3, 1, 1. 2, negative 3, 1, 1. And that gives you basically negative 1 times 2 minus negative 3. And that is equal to negative 1 times 2 plus 3. That's 5 times negative 1 is equal to negative 5. Okay. And A of 1, 3 is the same thing as negative 1 raised to the power 4 times the minor of this element, which is basically 1, 3 would be this element, delete this row, delete this column, 2, 1, 1, 1, 2, 1, 1, 1, and that is equal to 1 times 2 minus 1, which is equal to 1. Then you have A of 2, 1, which is equal to negative 1 raised to the third power times this minor 2, 1. So 2, 1 would be this element here, delete this row, delete this column, negative 1, 1, 1. Negative 1, 1, 1, 1. And then you have negative 1 times negative 1 minus 1, which is equal to negative 1 times negative 2, which is equal to positive 2. A of 2, 2 is equal to negative 1 raised to the fourth power times the minor 2, 2. So delete this column, delete this row, 1, 1, 1, 1. 1, 1, 1, 1, and this would be 1 minus 1, which is 0, so this is equal to 0. A of 2, 3 is equal to negative 1 raised to the fifth power times the minor 2, 3. minor 2, 3 would be delete this row, delete this column, 1, negative 1, 1, 1. 1, negative 1, 1, 1. Which is equal to negative 1 times 1 minus negative 1, which is the same thing as negative 1 times 1 plus 1, which is the same thing as negative 1 times 2, which is equal to negative 2. And a of 3, 1 is the same thing as negative 1 raised to the 4th power times the minor of this element, 3, 1. 3, 1. So the third row, the first column. So delete this column, delete this row, negative 1, 1, 1, negative 3. Negative 1, 1. And here I had a negative 3 and I forgot the rest. So I was doing negative 3, 1, 3 and 1, so negative 1, 1, 1, 1 and negative 3. So you have this determinant, so you have 1 times, so that is positive 3 minus 1, which is equal to 2. And a of 3, 2 is equal to negative 1 raised to the 5th power times 3, 2. So delete this column, delete this row, 1, 1, 2, negative 3. 1, 1, 2, negative 3. 1, 1, 2, negative 3. That's equal to negative 1 times negative 3 minus 2, which is equal to negative 1 times negative 5, which is equal to positive 5. And a of 3, 3 is equal to negative 1 raised to the 6th power times the minor 3, 3. Delete this row, delete this column, 1, negative 1, 2, 1. 1, negative 1, 1, negative 1, 2, 1. So you have basically 1 times 1 minus negative 2, which is equal to 1 plus 2, which is equal to 3. And so I can write some matrix, for example, D, as I'm writing down these numbers: 4, negative 5, 1, 4, negative 5, and 1, and 2, 0, negative 2, 2, 0, negative 2, and 2, 5, 3. 2, 5, and 3. And so if you now take the transpose of this matrix, which is D of dt, you would get the adjoint of A. That would be adjoint A, which is equal to this matrix as basically 4, negative 5, and 1, 2, 0, and negative 2, and 2, 5, and 3. Two, 5, and 3. So this is adjoint A. Now we wanted to calculate A inverse, and A inverse is adjoint A by determinant A. Determinant A is equal to 10, right? So therefore A inverse is equal to 1/10 times this matrix, which is 4, 2, 2, negative 5, 0, 5, and 1, negative 2, and 3. That is A inverse. So now let me check if my matrix is okay, and then we will continue with the rest. 1/10, 4, 2, 2, negative 5, 0, 5, 1, negative 2, and 3. That is okay. Okay. Now, we said that basically X is equal to A inverse times B. Now B is the same thing as 402. B is the same thing as basically 4, 0, and 2. And so we have this matrix. So you have 4, 2, 2, negative 5, 0, and 5, 1, negative 2, and 3, times, and of course you have 1/10 here, and you have another matrix 4, 0, and 2. So if you do this calculation, you will get 3 by 3, 3 by 1, so you get a 3 by 1 matrix. 4 times 4 is equal to 16, 2 times that's 0, and 2 times 2 is equal to 4. Negative 5 times 4 is equal to negative 20, and 0 times 0 is equal to 0, and 5 times 2 is equal to 10. 1 times 4 is equal to 4, plus 0, plus 6. So that's, of course, there is 1/10 here as well. So they have 4 times 4 is equal to 16, 0, and 4, and negative 20, 0, and 10, and 4, and 0, and 6. Okay. So I have 1/10 of 16 plus 4 is equal to 20. Negative 20 plus 10 is equal to negative 10. And 4 plus 6 is equal to 10. So you have basically 20/10 is equal to 2. Negative 10/10 is equal to negative 1. And 10/10 is equal to 1. And you can see that, of course, your x is positive, your y is negative, and your z is positive. X positive, y negative, which means that you are actually in the 1, 2, 3, and 4th octant, as we expected. So now we know that x is equal to x, y, and z, and that happens to be equal to 2, negative 1, and 1. And so you are, and that basically means that x is equal to 2, y is equal to negative 1, and z is equal to 1. That is the unique solution to this system of equations. And again, let me show you the graph one more time. So you can see that the solution is actually this point over here. This point over here, you can see that along the x-axis, your x is equal to 2. This is your x. Your y is equal to negative 1, which is this point over here. It corresponds to this point. And your z is equal to somewhere around 1. Somewhere around 1, which is exactly the coordinate of your z. Pretty powerful when it comes to the system of equations of 3 variables. Otherwise, it would be a little bit hard to calculate all of these numbers because you would have to, I don't even remember how we used to do this using other tools. I don't really remember that. But this is a much better system when it comes to these equations, provided that you know these rules of these determinants and matrices and everything. It's much easier and much more organized to solve these problems. So that was question number 12. There is a few more questions left here. We will do them in the next videos. Thank you.